Hi, everybody. Sorry, I'm a little bit late here. Let's. See, I'm gonna go to this guy. Sorry, guys, just 1 second. My class ran over last one, so I'm gonna need a couple of minutes here to. Oh. Okay, guys. Sorry about that. Can I get a quick sound check? Make sure everybody can hear me.
Yes.
Yeah.
Okay.
Yeah.
Thanks, guys. Sorry again. I was the last lecture ran a little bit over, so I'm having a hard time finding the lectures. So last time we went through. So that was the last of the sort of the introduction lectures where we talked about still the MOS transistor as being close to a perfect switch. And the idea there was that a NMOS transistor, when it's drawn like that, when the gate is equal to quote unquote a 1, then it's close switched between drain and source. And then when gate is a 0 or off, then it's an open switch. And then a PMOS when the gate is equal to 1, it's an open switch. And when the gate is equal to 0, it's a closed switch between source and drain and source. Okay, so this was our model so far. The only thing that we added to this was that an NMOS, so plus that NMOS drain to source or source to drain is good at passing 0. So this is from this node, the drain node. So from the drain to the source or vice versa. It's good at passing a 0, bad at passing a 1. Okay, and then vice versa for the PMOS from drain to source. So this is even when it's on, it's good at passing a 1 and bad at passing a 0. Okay, so that's the only thing we were thinking about these transistors. So starting with this lecture, we're going to be looking at what a MOS transistor, NMOS or PMOS, actually looks like. And we're going to look at its voltage versus current characteristics. And sort of in the following lectures, we'll work all the way back to, how is it that, and under what conditions can we use it as a switch? And why does this simple model work most of the time? But how and when do we need to enhance that simple model? Under what conditions? Okay, like for example, right now, so far we haven't talked about any transient performance, rise time, fall times, delays. We have to start looking at those. Okay. Well, this is sort of what's saying. Okay. All right. So the first place we start is with a MOS capacitor. So a MOS capacitor is an actual MOS transistor. I want to say this. Yeah, okay, I'll say it. So a MOS transistor has a source and a drain connection, but this is an NMOS. Okay, but let's say we start with something simpler. Let's just say we just hook up the drain and source together and hook them up to ground. Or let's just look at a real simplified model like this, where you have the gate poly, this is the oxide, and then you have the silicon substrate. And the reason it's a capacitor is because there is no source or drain, so it can't really pass. It's not like a 3-terminal device, so not a 3-terminal device. So it's not like you're using a gate to pass a signal through from source to drain. You're just using it as a variable capacitor. Okay, so under that condition, which again could be that you just hooked up the drain and source together, something like that, you have 3 areas of operation, depending on what the voltage on the gate is. So you do this, you put a voltage source on the gate. Okay. So in this condition, you have these three areas of operation. Okay. So remember that a P-type piece of silicon, okay, so a NMOS transistor that we're talking about here has a, let me, okay, so what do we got? We got a silicon dioxide gate. Gate oxide, I guess. Can you guys hear me okay? Sometimes I feel like I'm kind of whispering here.
No, you're good.
Okay, thanks. There's been enormous investment in my audio-visual setup. Well, not so much visual setup today, but audio. Anyway, so so here's a polysilicon gate. Polysilicon gate. And you can, for the first order, you can think of this as being a metal gate. First order. And then we had N plus source drains. And then we had a P sort of channel. Okay, and then we have a few other things, like we have a P plus connection. This is the channel, this is the body connection to the channel. So you need to bias the channel. Everybody good with this cross section? Everybody comfortable with that? You have to kind of like, this is one of the things you have to, I would suggest, you know, the tests are all open book, open internet, open everything. But if you have to like go and look all these things up, some things are just, you should kind of know. So anyway, so long story short, the channel is a P-type piece of silicon, okay? And I keep forgetting if we talked about this, but P-type silicon is a type of silicon where, you know, silicon, you have these covalent bonds. So, you know, if you're looking at this, these are supposed to be silicon atoms, okay? Because you have four, it's a group 4 element in the periodic table. So each atom has four valent electrons at the topmost shell of a silicon atom. It has 4 valence electrons, and because the way the atomic structure and shape works, it's going to have 4 neighbors, and so they all share sort of a covalent bond, so there's no extra electrons or holes floating around at very low temperature. Okay, then something you can do is if you implant this with something called acceptors. Okay, so if you implant it with like a group 3 in the periodic table element, and I think those will end up being things like boron, arsenic, are in group 3. Let me just look that up real quick. There. If I get that wrong, that might revoke my chip design card here. Where was I? Let's see if I can find this real quick. sorry guys, it would be boron or, actually it's typically just boron for acceptors. So for donors, so let's just keep it with this. So just say boron. Okay, if you implant this with boron, you guys don't have to remember any of this stuff. Obviously, I can't. If you implant it with borons, you end up, because boron only has 3 valence electrons, when you end up in a similar structure and you have silicon sitting next to a boron, instead of, so if I change this to a boron atom, oops, you end up missing a connection here, and that turns into so-called hole. Okay, so you end up with an excess of positive mobile charges in a p-type material. So these are all mobile charges, which in the form of these holes, and the holes are a lack of mobile electrons. You can think of it like that. It just seems like you have a sea of positive charges that can move around in a p-type material. And because the channel is a p-type material, it seems like there's a lot of positive mobile charges there. I didn't do a good explanation there, but is that, you guys are familiar with all these, with the concepts of holes, electrons, p-type material, n-type material, donors, acceptors, all those kind of things?
Yeah.
Yes, Professor.
Pretty much. Okay, cool. Okay, so sorry, that was a really long-winded thing of talking about why you end up with, in this channel, you end up initially with this sea of positive mobile charges under the channel. Okay, so this stuff. Okay, so when you have 0 voltage, you just have, you know, all these positive charges, and then when the voltage on the gate is a negative value, so you put negative charges here, they attract these positive charges even more strongly towards the gate. Negative charge attracts positive charge. You're creating an electric field in the gate. So it just really doesn't really affect anything. It just keeps piling on positive charges close to a gate. Okay, so this region is called accumulation. You're quote unquote accumulating these charges on the gate or on the other side of the gate. Okay, then you have this thing called depletion. So as the gate voltage now goes positive, so as you drive this positive, okay, notice what the positive voltage will do is, once you put positive charges here on the gate, you start pushing these positive charges away from the gate. Okay, so light charges are going to repel each other. So you're just basically creating a place here, a physical depth sort of underneath the silicon dioxide gate that is quote unquote depleted of these positive mobile charges, which are holes. Okay, and that keeps happening at this intermediate positive voltage. Then when you go past a certain voltage, when your inversion gets, your depletion region gets higher and higher, you get to this point called inversion, where the surface of the channel, quote unquote, inverts from initially being positive when we had no voltage on it to being negative. Which seems kind of magical. But what happens is, the reason this happens is, as we deplete this region, there are, just because you're above 0 degree Kelvin, you have thermal energy in your silicon, there's constantly electron hole pairs being generated in the silicon. Even if you have an intrinsic piece of silicon, means without doping, you constantly have these electron hole pairs that generate, and then they combine sort of in random mode. So you get an electron and hole pair, electron goes in one direction, hole goes in another, and sooner or later an electron will see another hole, they recombine. So you have this process in a piece of silicon called generation recombination. And depending on the temperature, this happens more and more as higher temperatures, as you get to higher temperatures. I mean, temperatures above, minus 277, whatever, Celsius. So essentially any temperature, you have this generation recombination. But what happens is, when you have this depletion region, normally generation recombination there's no current, because you generate electrons, you generate holes, they float around and they recombine. So all this stuff is happening, but there's no net charge ending up anywhere. Okay, but because we have an electric field, we have a plus electric field at the gate, it tends to attract the electrons that got generated as part of this generation recombination and repel the holes. So what it's doing is actually it's attracting, instead of these electrons just recombining with holes in the depletion region, they actually start bubbling up, getting attracted towards the gate because of this positive charge on the gate. And the holes that get generated here get pushed out because of that same electric field into the substrate. So basically what happens is you end up with this layer of electrons right underneath the gate. Once that happens, when this region, this depletion region, is big enough that you basically create enough electrons, and then you sort of create the situation where you have this inversion. So you go from positive charges on the other side of the gate, on the silicon part of the gate, to negative charges on the silicon part of the gate. Anybody have any questions about that? Okay, that's probably the deepest we're going to go in terms of okay. Okay, now let's say we add a source and drain to this. Okay, so we have these guys, okay, these cases. I'm gonna actually duplicate this to get myself into more trouble. So I'm gonna go and add a source and drain to this. So this is N plus, N plus. Okay, so in the case of, in these two cases, well, essentially, yeah, in these two cases, you really don't have a path for the source to talk to the drain. Okay, so this would be the drain. This would be the source. So this is all sort of a cartoon drawing, but hopefully you guys get the idea there. Because what happens is, if this is N plus and this is P, this looks like a diode right here. So we have a diode here and a diode here. So it looks kind of like this guy. Looks like, hopefully this isn't confusing you guys too much. Source. Okay, so we got two, so the diodes are preventing you, depending on, let's say the source and drain now are positive voltages. So source, so let's say they're both greater than or equal to 0. Okay, and then let's say this, the body voltage is equal to 0. So if we assume all that, which is how, you know, our circuits are going to operate, the drain and source to, in these two cases, these drain source diodes to the channel are going to be reverse biased. So you won't get any current going one way or another. It just can't happen because of those diodes. Okay. But in this case, in the case of inversion, now notice I have N minus here. It doesn't look like I have a P-type there. It looks like I have an N-type material there. So it just looks like a, I don't know, it looks like maybe like a resistor from this N plus from source to drain, and all of a sudden I can conduct from source to drain. Okay, as soon as I get into this inversion point. But I can't communicate between source and drain. I can't get a current before that point. Okay, so what happens is, I'm looking for my, there we go. So we end up with these three modes of operation, depending on our gate, drain, and source voltages. Okay, again, caused caused by this effect of going between accumulation, depletion, and inversion. Okay, and the reason why, you'll see why we were looking at, instead of the gate, we're going to look at the gate source voltage. Okay, so from the gate to the source. Okay, the reason for that is, for an NMOS transistor, we pretty much assume that the source is kind of is connected to the ground. Okay, remember all our pull downs, which were NMOS, were connected to ground, and pull ups, which were PMOSFETs, were connected to supply. Okay, so we look at the gate source voltage. Well, we always look at the gate. So I'm trying to give you guys like a visual to why we're looking at VGS, but never just look at the gate. Always look at the gate source or gate drain voltage, and you'll see why that's the case in a second. But anyway, you end up with three modes of operation, and it depends on these voltages. Okay, the gate to source voltage, the gate to drain voltage, and the voltage between drain and the source. Okay, and then depending on these voltages, we end up in these three regions, which is cutoff, linear, or saturation. Okay, so in cutoff, what happens is we are in accumulation mode. Okay, we're in this mode from a gate standpoint. Okay. In linear and saturation mode, we're in inversion. You can think of this this depletion being, you can either think of that as still being cut off or think of it as an intermediate region. But if you're in depletion, you're still, so let's say or depletion. So in either one of those cases, there is no connection between source and drain. So we call that cutoff, or you can think of it as a transistor being off. And when you're in inversion is when the transistor is on. But when the transistor is on, it could either be, so transistor is on, and MOS is on, but you could be either in linear, quote unquote, or saturation modes, and we'll define what those are depending on VGS, VDS, and threshold voltage. Okay, so one last thing is, if you noticed in the layouts and in all our sort of cartoon cross sections, etc., the drain and source are symmetric, right? So when we draw a transistor, it always looks like we have source, drain. So that's the gate oxide. This is the poly. So how do you decide what is the drain, what is the source? And by convention, what we say is that the lower voltage is the source. Okay, so the lower voltage for an NMOS. So if this is the gate, if the source is if this node is connected to ground, this node could only be at ground or higher. So we call this the drain, we call this the source. The PMOS is the opposite. Okay, if this node is connected to VDD, this node could only be at VDD or lower. So we call this the drain, we call this the source. And that's by convention. Okay. All right, so let's walk through these. So again, with when the gate source voltage is 0, okay, and but this is when the gate voltage is 0, or sorry, it doesn't matter what the gate drain voltage is. When the gate source voltage is 0, okay, and then by convention, again, the body we connect to, actually it's not by convention, but the body we connect in an NMOS, we want to connect it to the lowest voltage in the circuit, which is ground. Okay, so we have it connected to the source, at least in this transistor case. And so when V gate source is 0, we're in accumulation. Meaning that you have these positive charges separating the source and the drain, so you end up with 0 drain source current. Okay, because the source and the drain, we got these two diodes from the N plus to the P of the channel that are isolating them. Any questions so far, guys? Okay, so the next step is when we're in linear mode is when we've already inverted the channel. So it's already in inversion mode, or channel is inverted. Okay, so we have negative charges around the channel. So we have a connection between source to drain. Okay, and in this mode, now you've got a connection between source and drain. Now we start looking at the drain and the source voltage, and it basically looks like a resistor now. As the drain voltage gets higher, you get more current. So the drain source current just increases pretty much linearly with drain source voltage. Okay, so it looks like a linear resistor, and that's why we call it this linear operating mode. Okay, but the channel is inverted in this mode. Okay, so this is the next one. So here, your channel is still inverted, theoretically, or was inverted. So it's like you were in linear mode. But what happens is as this drain voltage increases, okay, so initially, let's say the drain voltage was at some value, right? It wasn't too far from ground. So you basically had IDS when VDS is less than some, let's call it VDSAT. We'll see how we define VDSAT. When VDS is less than that, then IDS, drain source current, is sort of proportional to V to drain source. Okay. When the drain source voltage goes bigger than this certain voltage, VDSAT, again, that we'll define, what happens is this channel is not now, isn't continuous. You get a certain voltage here. Remember how we got to this inversion was the voltage. So the voltage, this charge is here, or this voltage here versus the voltage on this channel. Now the voltage on the channel was the same here before we added a drain or a source, because it was all defined by here. But because we added a drain and the source, as we increase this voltage on the drain, as we increase this voltage towards the gate, this sort of gets, you can think of it as getting less and less inverted. Okay, so you have this strong channel here because you have a very large electric field here, but you have a smaller electric field here. Okay, and at some point it sort of pinches off, but because you have enough electric field, and again, this turns into kind of a hand-waving explanation for this class. It'd be sort of more clear if we were in a semiconductor sort of physics class. You basically, the current becomes independent of VDS at a certain point. So you pinch off the channel, but you don't eliminate the drain to source current, because this current still goes to here, but it jumps across to the drain because there's enough electric field to do it. Again, we won't get into that. But basically what happens is the drain source is now independent of VDS. Okay, so this is linear. This is saturation. Okay. Let's see if actually there's any. Let me see if there's any nice. No. I just want to see if there was any kind of a, what do you call it? A nice, of course, now I'm stuck here. Sorry, guys. There we go. Does everybody kind of follow me so far?
Yes, Professor.
Yeah.
What's that?
Yeah, we following.
Okay, great. Thanks. Okay, so now let's look at the, so what does this mean in terms of if you look at the IV characteristics? If you guys remember the IV characteristics of a transistor, we're looking at, I'm assuming you guys all had sort of a MOS physics class, but there's two current versus voltage characteristics because we have three terminals. Okay, we have a gate terminal, drain terminal, and source terminal. Okay, so one, and we have these graphs we draw are two-dimensional, right? Voltage versus current. So one graph we can draw is the gate source to I sub D current. Okay, the other graph we can draw is the drain source versus I sub D current. Okay, for the same transistor. Here in this graph, because gate source is variable, we're going to assume VDS is constant for the lines we draw here. Okay, for whatever we draw here, because the drain source is a variable, we assume V gate source is constant. Okay, so let's draw what happens in the linear region. Okay, again, and we're going to draw the gate source versus IDS, and sometimes we draw the drain source versus the IDS. Okay, so let me open this up here. Let me just open up something. Okay, so I think the question is, what's happening now in the linear mode, linear operation? Okay, so that depends on how much charge we have in the channel. Okay, and so that is pretty easy when if you're looking at the channel charge, right? Because we just said it looks like a capacitor. So we have silicon dioxide, and then we have it's polysilicon, but let's call it a metal or conductor. And then we have the channel, the P channel. And then we have the source and the drain. Okay, so when we have, and remember in the case we're looking at in linear mode, we're in inversion, okay? Meaning that we have like negative charges right up against the silicon dioxide. That means that we basically, this gate looks like a parallel plate capacitor. Okay, looks like a parallel plate capacitor with the thickness of the oxide being just the silicon gate thickness. So the thickness of the silicon dioxide, okay? And the model for the capacitance of the parallel plate capacitor, which is not even well drawing it. You can kind of see it drawn here better than I can draw it, okay? Is the dielectric constant of silicon, or sorry, of oxide, times the area of the plate over the thickness of the oxide. Okay, so this is area. This is the separation between the two plates. So it's just the equation for parallel plate capacitance with dielectric being silicon dioxide. Okay, so we can sort of shorthand write this as C is equal to C ox W times L, and C ox is defined as dielectric constant of silicon dioxide over the thickness of the gate. So you'll see this again and again. So we have so this is the equation. This is the equation for a parallel plate capacitor, but when you're doing a design, you don't want to do this calculation of, you don't want to pull up epsilon oxide every time. You have to go look up, these constants in their sort of funky numbers with lots of digits and, scientific notation, etc. And then for any particular design you're doing, the thickness, remember the thickness of the gate oxide is constant for any given process. So if you're doing a design, you already know what process you're in, you just want to do this calculation once, this epsilon ox over T ox, the thickness of the oxide, is like a constant for any given process, for any. Okay, but what is variable is the width and length of the particular transistor that you're working with. Okay, so that's why you basically create this thing called COX, which is just the dielectric constant of silicon dioxide over the thickness of the oxide for the particular process you're in. And then from then on, you just use it and you multiply it by the width times length of the transistor you're considering. Okay, so that ends up being the capacitance. Okay, then the next thing you want to consider is, okay, well, what's the voltage between sort of drain and source that you're looking at, or the voltage at any point here along the channel. Okay, so that voltage is, I just draw it over here. So this voltage is the gate to channel voltage minus the threshold voltage. Okay, so the threshold voltage is defined as the voltage. So it's defined as the voltage where you go, so V sub t defined voltage when you go from cutoff to inversion, or from depletion to inversion, depending on what you want to look at. Okay, so that's a voltage that you need to overcome before you have a channel. So when we're looking at the voltage in the channel, we are we have to subtract this threshold voltage because we have to be at that value or higher to have a channel to begin with. Okay, so we basically get this gate to channel voltage minus the threshold. And when we're in linear mode, we're just going to assume that the voltage of the channel is half, which is basically on the average ends up being, so this gate channel, so I'm going to write it down somewhere else. Because we're in linear mode, because linear, assume on the average that V gate channel is V gate source minus V drain source over 2. Okay, so that's what this voltage at any point, basically your voltage, channel voltage ends up being V gate source minus V drain source over 2 minus VT. Okay, so that's the charge in the channel. Okay, when you're in linear mode. Okay, so then the next thing we want to see is, remember, let me take a step back about what we're doing. Okay, remember one way to look at it is, so Q is equal to CV, dQ dt is C dV dt. Okay, and this is current. So if we want to find, this is what we're trying to find. We're trying to find this current, right? We're trying to find this current. We just looked at the capacitance, okay? Then we looked at the voltage. So we got those two. Now we need to look at how fast are these charges moving. And then once we have that, we have the capacitance, we have the voltage, and find out how fast they're moving. Now after that, we can get the current. Okay, so so here we are. So we have basically electrons in an NMOS. So this whole discussion is about NMOSFETs. The PMOS ends up being the inverse of that. But so those are electrons, okay? So, and then basically we have this electric field between the source and the drain. So this is more positive than this. So the electric field is going to be going in that direction and it's going to push the electrons across. So basically the electric field in the channel ends up being the drain source voltage over the length. The channel length is the actual physical separation between drain and the source. Okay, and then the second thing we have is we have so that electric field gives these electrons a certain speed. And the relationship between a speed of an electron and the electric field is called the mobility. In this case, it's the electron mobility. And it's just a definition of this. So if you had an electric field, you had velocity there. As the electric field increases, your velocity would go up, and the slope is this mobility, mu. And later on, we'll talk about how this will like sort of flatten out. But for the time being, we're just assuming it's related. Okay, so basically, this velocity is the length of the channel divided by the time to go across the channel. So the time, we just solve for the time, is a channel length over this velocity. Would be, just write it like that so it doesn't get confused with voltage. Okay, everybody follow me so far?
Yeah, we're following.
Okay, great. Okay, so now let's look at the current versus voltage characteristics. Okay, so we know the charge. And we want to, let's see. Sorry, guys. Just give me 1 second here. My iPad is sort of mangling my. Hopefully you guys can follow along. My iPad tends to mangle my PowerPoint, so I have to double check here. Okay, so basically the current, going back to this, is that the charge in the channel divided by the time for these, the charge to get across the channel. Okay, so going back to this, the time to get across the channel is the velocity over the length. Velocity is mobility times the electric field over the length. Okay, and electric field is VDS over the length. Okay, so this is going to mu V ds over, wait a minute. I get this right. So T is, oh, sorry, L over V. What am I doing? Length over V. So we end up with, sorry, L over mu E. E is VDS over L. So we end up L over mu VDS over L. I'm getting too much. Let's see. am I doing
Professor,
wrong
is it
here?
supposed to be blank on the slide deck you sent out? Because like,
No, if what you do is you gotta like put it in play mode.
oh, I see. So it has multiple stages. Oh, I see.
Yeah, yeah. So yeah, you guys gotta put it in sort of slideshow mode. Okay. So that's the time, and then the channel, the charge, we know what it is, right? So we calculated that. So let's put it all together. So we had the channel charge was this guy, right? It was Cox WL. So there's a channel charge, Q channel. Okay, time we got here. So 1 over, I'm just gonna sort of do the risky move of doing it. So it's 1 over time. So I'm gonna invert that, end up with mu VDS over L squared. Okay, and then the VDS, we just said we're gonna use this. So this is a channel charge. So we're gonna VGS minus VDS over 2 minus VT. Okay, so we basically end up with mu Cox. I'm just removing stuff around. W over L, B gate source minus VT minus VDS over 2 times VDS. And then we're gonna, again, because we're gonna be, we're gonna assume that, we're not gonna assume, by the way, but it's gonna be the case that mu Cox is gonna be constant. And we wanna basically just look at the voltages. We're gonna call everything beta. So this is like a sort of a trans, you can think of it as a gain. So mu, this is just by convention, you're gonna call beta mu Cox W over L. So we just end up with this beta times all the voltages. E gate source minus a VT minus VDS over 2 times VDS. Okay, so that's the equation when you're in the linear mode of current versus voltage. Some things doesn't seem quite right here. So let me, but anyway, I'll see if I need to troubleshoot this real time. But so let's go to the next one. I'll just double check this after the lecture just to make sure we didn't miss anything. But now let's look at in saturation, what happens. Okay, so if we said if the gate drain voltage ends up being less than a threshold. So remember we have n plus, n plus. This is the drain. This is the source. And this is the gate. If around close to here, so here our gate source voltage, because the source is at ground, our gate source voltage we know is, if we're on, if we're in saturation, we know we're inverted, we know this is higher, this gate source voltage is larger than VT. We know that because by definition we're on. But here, by here, right at the drain, so we have the gate drain voltage, it might be below a threshold. And that's when you have the pinch off happening and you're in saturation. Okay, and that happens when the drain source voltage is larger than this VD sat value, and then VD sat, we talked about VD sat last time, VD sat is equal to VGS minus a VT. Okay, so in this case, we basically end up, I'm just going to rewrite the equation we had from the last page from the linear mode. We had VGS minus VT, sorry, minus so this was VDS, but we're going to substitute this value for VD sat for VDS. Okay, VD sat. Because after that point, the ID doesn't change. Okay, so this ends up being, and then I'm going to substitute VD sat. Basically substitute this equation into VD sat, and you end up with beta over 2 VGS minus VT squared. Okay, so the key thing here is that notice that IDS, we got rid of any, so there's no VDS term here in saturation. Okay, you basically are only dependent on V gate source. Doesn't matter what happens to VDS. So that's why we call this saturation and this linear, because this guy, we still have VDS terms. So current is still proportional to VDS. Okay, but here there's no dependency on IDS with VDS. It's only the gate voltage, gate source voltage. Man, this looks totally mangled. Sorry, guys. Okay, so what this should look like is this. Okay, so now these are all the components. Again, this is in your slides, but let me, my thing is doing VGS. I think it just doesn't like symbols. Okay, so this is the important thing we should remember. And this is a summary of these currents we worked out in the previous slides, okay? So we have these three modes of operation. We have this cutoff mode. So here the transistor is just off. Before the gate source voltage is below a certain value called the threshold voltage, the transistor at no point in the channel is an inversion, means that the drain and the source are totally cut off from each other. So it's called the cutoff region. Then after a certain point, when the voltage of the gate source gets past that threshold voltage, you basically turn on. And now, depending on the drain, so the relationship between the drain source voltage and the gate source voltage. So if this happens, if, well, it says here, VDS is less than VDSAT. And remember, VDSAT is defined as V gate source minus VT. So this VDSAT is sort of a moving thing, moving bias condition, depending on what your gate voltage is and drain voltage is, this VDSAT changes, okay? So, VDSAT only changes from the gate voltage, but your VDS being less than that is a function of the gate source voltage also. So in this case, okay, your transistor is on, but you're still proportional, your current is still proportional to VDS. Okay. In this case, then VDS is greater than VDSAT, okay, you basically have no relationship to VDS and you're in saturation. So what does that look like? Let's try to do a plot. Actually, let me do it on the, try to do it here. Okay, and we're gonna try drawing a plot of sort of, this is the, again, NMOS, and let's try to plot VDS versus IDS. Okay, and now remember, we have to hold V gate source constant because we have 3 terminals and it's a 2D graph. So for each VGS value has its own curve. Okay, so let's take the curve of VGS when, let's say VGS is 0. Okay, so what does things look like? So if VGS is 0, that means we're in this cutoff region, means that there is no current. So this green would be your curve. Okay, as VGS increases, those curves are just going to lie on top of each other until VGS equals the threshold voltage. Okay, past that point, then the transistor is going to turn on. Okay, so this is all the curves. So green is all VGS less than VT. They're all going to be 0, sitting on top of each other. There's no current, regardless of what VDS does. Okay, so now let's say V gate source is greater than VT. So we're in these 2 modes. Now we're going to look at the relationship between VDS and VGS to decide where along this axis we're in linear and where we're in saturation. Okay, so let's say VGS is relatively low. Let's say it's sort of like 1 volt or something. Okay, so VDS, and let's for the sake of discussion say VGS is equal to 1 volt and VT is equal to 0.7 volts. Just for the sake of, okay, just for to draw something. Okay, so what happens is this says that VDSAT is 1 volt minus 0.7 volts. Okay, so that is around here is equal to 0.3 volts. So anything less than 0.3 volts is linear. So we use this equation, which kind of looks linear, although it's got this funky sort of second order effect on VDS. So it looks kind of linear, but give it a curve. And then after we hit VDSAT, it flattens out. So this curve is, for example, VGS is equal to 1 volt, for example. Okay, now let's say we use the same example, but now you want to drive VGS is equal to 2 volts, say. Okay, now VDSAT changes because we're at 2 volts minus 0.7 volts or 1.3 volts. So this breakpoint moves from 0.3 volts to 1.2 volts. So you end up with this curve. You're in sort of you're in this quote unquote linear mode up until you hit this VDSAT value and then you flatten it. So this is for VGS is equal to 2 volts, for example. So you're holding gate source voltages constant and basically you're adjusting VDS. Okay, so those are the family of curves, what they look like. So let's stop here, guys, and then we'll follow up next lecture with a example of what that looks like. Any questions? I know that was getting pretty complicated, but I think the main thing you guys need to remember are basically these relationships of
Professor,
What's that?
do you save all notes you write it right now? Because when we downloaded the PowerPoint, it doesn't show it. We can't see as a just video, yeah?
I got you. I have it saved. I'll just upload it so you guys can get it.
Okay, yeah, but we can watch it as a video too.
Okay, I'll put it up. It just might get a little confusing because I'm writing as I talk, but anyway, I'll put it up for you guys.
Yeah, thank you.
Sure. Any other questions?
Yeah, with those curves that you have, like for different values of VGS, when it's in like the saturation region, which is like the flat region, right?
Yep.
It has like some sort of slope, right? It's not like completely flat.
Yeah, it has a slope, but
And that's based on some weird value things that like.
well, it's actually it's not terribly weird, but we'll get to the slope probably in a couple of lectures or maybe the next lecture. But there is a slope. It's not absolutely flat, but you're right. There is a slope.
Okay.
Yeah. So and it's kind of like it's a slightly high going slope. Yeah. Any other questions? Okay, guys, I'll talk to you on Thursday. Take care.
Thank you, Professor.
Thanks.
Have a good one.
Thanks. Bye.
Thank you, Professor.
Thanks.
Yeah, thank you, Professor.